see that okay?
We can.
Yeah, good. Okay, yeah, so I'm going to speak today about I guess, environmental non-additivity. So this is situations where we've got a system coupled to multiple environments, and those environments may be strongly coupled, or at least one of them may be strongly coupled to the system in such a way that the influence of the environments is not just additive. They don't just act as in the way they would if they were independent and coupled to the system on their own. And I'll talk about a few different aspects of this non-additivity and where it might be important in a thermodynamic context as well. And so this talk is based on a number of different works. So I should say thanks also to Henry, Connor, and Dave, who are former PhD students of mine, and Jake, who's also at the University of Manchester, and Florian, who's at Imperial, who've all been involved in different aspects of this work. Okay, no, it's not letting me go forward for some reason. That's okay. So just to outline, I'll start with a brief kind of introduction and motivation. So talk a little bit about open quantum systems and why we're interested in non-additivity in multiple environments. I'll overview the collective coordinate master equation, or sometimes known as the reaction coordinate master equation. This is probably quite well known already to a number of people in the audience, but I thought it might be useful just to go over the basics. And this is a method for dealing with systems that are strongly coupled with their environments, so they can build up correlations with the environment, for example. And I'll talk a bit about the generation of system reservoir correlations. Another useful aspect of the collective coordinate approach is that it quite naturally allows us to consider situations where we have multiple environments and non-additive contributions, as I'll explain. I'll then talk a bit about heat engines at finite coupling. In particular, the reaction coordinate mapping allows us to dephase our heat engine even when it's strongly coupled to its heat reservoir. So the working system is strongly coupled to the heat reservoir. And I'll say a bit more about that, but what that means in terms of the dephasing is that there's no energetic contribution, which the reaction coordinate approach allows us to identify how to do that even at strong system environment coupling. And then I'll go through some examples of non-additivity when we have systems that are naturally coupled to more than one environment. So a kind of two-level emitter that's strongly coupled to vibrations and weakly coupled to an electromagnetic field. So that could be a solid state single photon source, for example. And then transport situations, so strong vibrational coupling in a quantum dot system, for example, that's also coupled to fermionic leads. And I'll talk then a bit about counter statistics in that situation and thermoelectric performance. Okay, so I deal with open quantum systems in terms of master equation approaches generally. So I thought I should very briefly set the context by talking about master equations. So we imagine we have some system and it's coupled to its environment, as you can see on the right-hand side. So the Hamiltonian contains terms that relate to the system itself, to the environment, and to their mutual interactions. And master equation approaches, as many of you will know, are first order differential equation approaches that describe the time evolution of the system of interest rather than the full unitary evolution of the system plus environment. So what that means is we trace out the environmental degrees of freedom in some manner, which generally eliminates information on the environmental state. Usually we only approximately retain the influence of the system, of the environment on the system. Generally, it's not possible to retain the full influence non-perturbatively except for some very simple solvable models. So we have, one advantage, though, of course, is we end up with a reduced description, which is only in terms of the system state. So it's generally quite intuitive and efficient and straightforward to work with. And we can get quantities, for example, like energetic shifts or decay rates that we can relate directly from Hamiltonian parameters to experimental observables. So we can also quite easily test the accuracy of our models experimentally as well. But as I've mentioned, tractable master equations nearly always require some kind of approximation unless the model itself is very simple. So they're often valid only for quite restrictive parameter regimes. So the textbook Born-Markov methods, for example, will treat the environment as remaining in thermal equilibrium at all times. And the explicit kind of generation of system environment correlations is usually ignored, at least as far as the system's concerned, in the description, which is valid at weak coupling between the system and the environment. For an experimental progress, this is no longer satisfactory, I suppose. So it works very well in the regime of kind of standard quantum optics, where a lot of master equation approaches were developed and applied. But for solid state systems, for example, the collective degrees of freedom of the system can often be much more strongly coupled to their surrounding environment. So these kind of weak coupling Born-Markov treatments, the approximations are too severe and they may not work. And so we need to think about other ways we might describe the dynamics of the system if we want to maintain a master equation approach. From a purely theoretical perspective, from the point of view of this talk, it's interesting to ask what we can say about thermodynamics at strong coupling if we relax these assumptions and allow, for example, correlations to build up between some system and its surrounding heat reservoir. So to say a little bit about what I mean on non-additivity of multiple environments, so you can see schematically here, we might consider some system that's simultaneously coupled to two different environments. This kind of situation arises naturally in many different situations. I already mentioned a couple in the outline and introduction. One example from a thermodynamic perspective is, of course, in autonomous heat engines and refrigerators. But I also mentioned situations, for example, of solid state emitters and then in non-equilibrium transport in quantum dot systems or molecular nanojunctions. Now, within the master equation formalism, if we make weak coupling Born-Markov approximations, then that naturally treats the environments as being additive. So what that means is we end up with a master equation that has a kind of standard form where these dissipators that describe the action of environment 1 on the system and then the action of environment 2 are just added in the master equation. So these are unchanged from how they would be if the other environment wasn't present. So that's what I mean by them being treated additively. Now, within the limitations of the Born-Markov approach, that's perfectly fine. That's what arises naturally if you go through the derivation. But if one or more of the interactions between the system and environments is strong, then this is no longer really a valid approach. And I'll talk a bit later about if we just phenomenologically enforce additivity in that kind of situation, we can find some somewhat bizarre behavior, so non-physical behavior, in fact, things like breaking the Carnot bound in thermoelectric transport, or even non-physical current flow in a nanojunction where there's no temperature or voltage, no temperature gradient or no voltage bias. So it should be an equilibrium situation, but current flows nevertheless if we enforce additivity. Oh, I'll just go back there. So here's a couple of examples just to give a kind of experimental and physical context, I suppose. So On the left-hand side, there's a kind of diagram of a semiconductor nanostructure. So this is, well, happens to be a double quantum dot, but it could just be a single solid state 2-level emitter, for example. And we've got some incident electromagnetic excitation. The system, the dots, can emit photons, and that gives rise to an observable signal, but they're also embedded within a bulk structure, and lattice vibrations then can be quite strongly coupled to the discrete electronic states of the dot region. And so we have a situation where we need to account for that strong coupling to the bulk phonons, but we also have simultaneous weak coupling to the electromagnetic field. And I'll talk about that as an example a bit later. On the right-hand side, there's a schematic of a molecular nanojunction. And in a similar way now, we've got strong coupling to the vibrations. So these could be the molecular vibrations, for example, or if the central region was some kind of quantum dot, it could again be coupling to bulk phonons of some sample. And here we'll consider weak tunnel coupling to fermionic leads. So there's a current potentially flowing through the system, but an influence of strong vibrational couplings simultaneously as well. So the kind of technique I'm going to use will map between the original representation that I showed on a previous slide to this new representation, which will allow us to include some of the effects of non-additivity between the two environments. So we imagine we've got a situation schematically where we've got a system coupled to two environments as before. Let's assume one of the environments is strongly coupled to the system, and the other environment is weakly coupled to it. We're going to map using the collective coordinate mapping to a situation where we enlarge our system to include a collective mode, so some collective degree of freedom of the environment that the system is strongly coupled to. And then after that collective mode mapping has been performed, we're going to assume that the residual environment that's left over is now only weakly coupled to this enlarged augmented system. And so then we'll trace out the residual environment in the standard Born-Markov approach, but remembering that we've included a collective mode into this enlarged system. And so we still capture the dominant strong coupling and non-Markovian features of the system environment interaction, despite tracing out the weakly coupled residual environment. The other environment that we're always considering to be weakly coupled to the system is now weakly coupled to the enlarged augmented system. And so its influence, although treated in a Born-Markov approach, is now derived with respect to the full eigenstructure of the enlarged system and collective coordinate. And so it is aware now that the system is strongly coupled to another environment through that mapping. And what that means is then we capture non-additive effects between the two environments, between the weakly coupled environment and the strongly coupled environment in their influence on the system. So this mapping will allow us to naturally incorporate the non-additivity, and it also allows us to incorporate to a certain level environmental dynamics and the accumulation of correlations between the system and the strongly coupled environment. Okay, so here's a little bit more detail on the collective coordinate mapping. So let's just consider a single two-level system to begin with for simplicity. And it's coupled to some collection of harmonic oscillators. They're drawn as discrete here, but that needn't be the case. It can be a continuum bath of harmonic oscillators. And we're going to perform a normal mode transformation that takes us to this reaction coordinate or collective coordinate representation, where we now have the two-level system that's coupled only to a single collective mode, the reaction coordinate. But that mode itself is then coupled to a collection of independent harmonic oscillators that make up the residual environment. So from a perspective of the Hamiltonian, we've got some term that couples the system linearly to the bath, and that is then mapped to a term where the system now couples only to a single collective mode, with that mode being defined by the normal mode transformation on the original environment. So for something like the spin boson model, which is a model obviously that we come across frequently, particularly in open quantum systems and in quantum thermodynamics as well. This is the way the mapping acts. So we've got a system Hamiltonian that gives us some bias along Z and then some tunneling element along X, a bath of harmonic oscillators, and then a coupling between the two-level system and the position essentially of the harmonic oscillator bath. As I've said previously, this term is mapped to our collective coordinate. So now we have a single oscillator that couples to the two-level system. The mapping does nothing to the system itself, so that's left unchanged, but the normal mode transformation will now map all the harmonic oscillator modes that were initially independent in the original representation, such that we now have a collective coordinate with its internal Hamiltonian, and then our residual bath, and then there's a linear coupling between the collective coordinate and all the modes of the residual environment. And as I mentioned previously, we trace out the residual environment within the standard Born-Markov approach, but we treat the system coupled to the collective coordinate exactly. And once we do that, of course, if we want to look at just the properties of the system, then we can take our description of the enlarged system plus collective coordinate and just trace out the collective coordinate to get the system dynamics. So here's some examples to show you that this reaction coordinate master equation does work. So on the left-hand side, in both plots, I'm plotting the population of the two-level system here as a function of time, assuming that the system starts in its excited state. On the left-hand side, I've got a situation where the coupling is relatively weak, so it's an order of magnitude smaller than the internal energy scales of the system. But I've chosen a bath spectral density that gives rise. So the spectral density is a measure of the system bath coupling weighted by the environmental density of states. And I've chosen a spectral density such that that translates into a long correlation time of the environmental correlations. And so although the coupling is relatively weak, the weak coupling approach, the Born-Markov approach, fails. It breaks down because the Markov approximation is no longer justified. The correlations are too long-lived within the environment. However, we see that the collective coordinate master equation agrees very well with our numerical benchmark, which is based on the hierarchical equations of motion approach. So for those unfamiliar with the hierarchical equations of motion, you can just think of it as a set of, well, as the name suggests, a hierarchy of equations of motion that describe the dynamics of the system and its correlations with the environment. And for certain situations and certain spectral densities, it can converge very nicely to numerically exact results. So we use that as our numerical benchmark. On the right-hand side, similarly now we've got strong coupling, much stronger coupling between the system and environment, but again, a strong correlation time. So we certainly wouldn't, a long correlation time. So we certainly wouldn't expect the weak coupling approach to work well here, and it doesn't. But encouragingly, the collective coordinate master equation still captures very well the numerical benchmark dynamics. And I should say that although I've only shown populations here, the coherence dynamics is similarly well captured in these situations as well. So one thing that this approach allows us to do is to go beyond just looking at the system, the reduced system dynamics itself, and probe something about the system reservoir correlations as well, at least approximately, because we can look at the correlations that build up between the system and the collective coordinate and use them to give some kind of lower bound, although it may not be a very tight lower bound on the correlations that that build up between the system and the full multi-mode environment. So that would be the system and the environment before the mapping is performed. The mapping is unitary, so of course that the dynamics is the same formally before and after the mapping, but our approximations are applied differently after the mapping, of course, in the master equation approach. So if we look at the mutual information between the system and the collective coordinate, which is written here, and it's plotted on the right-hand side for the same parameters that I just showed for the system dynamics. And we can see that there's two timescales at play here. There's a short timescale where there's a kind of oscillatory sharing of correlations between the system and environment. And this is a timescale that's associated really with the sort of transient non-Markovian behavior on timescales over which the Bath correlations are significant. This dies away, but over longer timescales, correlations do accumulate and they build up such that they remain present even in the steady state. And that's also true at stronger coupling, although the transient timescale is a bit shorter here. But again, we have correlations that are persisting in the steady state and actually a larger level of correlation for stronger coupling. So yeah, as I mentioned, the system environment correlations persist into the steady state. And what I'm showing on the left-hand side there is the mutual information in the steady state as a function of coupling strength. And we can see that it's monotonically increasing. The crosses here are given by a thermal state, but it's a thermal state in the mapped system plus collective coordinate eigenbasis. So the system state itself, if I were to trace out the collective coordinate, is no longer in a thermal distribution over its own eigenstates. So the eigenstates of the system, the isolated system Hamiltonian. So in that sense, it's non-canonical as far as the system itself is concerned. Instead, as I said, we have a thermal state now of the enlarged mapped Hamiltonian. So that's what the crosses represent here. The line through it is just propagating out the master equation into the long time limit. And so we see that the two do agree. So it does appear that dynamically the system approaches this thermal state of the mapped Hamiltonian. So that thermal state is given here. So it's, as I said, it's in the enlarged space of the system plus collective coordinate. So the Hamiltonian here is the Hamiltonian of the system plus collective coordinate, and then the temperature scale is set by the temperature of the residual environment, so the part of the environment that's assumed to remain in thermal equilibrium. And just to emphasize, if I were to trace out the collective coordinate, I would not now have a thermal state of the system itself with respect to its energy eigenbasis. So some of the consequences of that are shown here. So we're looking at the ratio of the ground to excited state in the system, the isolated system energy eigenbasis in the main plot as a function of the system environment coupling strength. And we can see that that ratio decreases as the system environment coupling is increased. But in the weak coupling case, of course, we would not see any change at all, because the canonical thermal state of the two-level system doesn't have any dependence on the system environment coupling strength. It just has a dependence on the temperature. Likewise, in the inset, I've shown that coherences can accumulate in the steady state within the system energy eigenbasis as the system environment coupling is increased. And again, this would not occur for the standard canonical thermal state for the two-level system, which is always diagonal in the system energy eigenbasis. So the weak coupling approach here shows no coherence in the long time limit. And as before, we benchmark the collective coordinate master equation against the hierarchical equations of motion that we propagate out to long time. And we see that the two, again, agree very well, even in the long time limit. So these coherences then that are present in the system energy eigenbasis in the long time limit are dynamically generated due to the strong system reservoir interactions, taking us away from the system thermal state in the long time limit. Okay, so you can probably see then that that there could be some interesting implications of that for thermodynamics, and I'm going to show an example here for a heat engine, actually at finite coupling, so an Otto cycle, where we assume that we have a two-level working system, but that it can be coupled strongly to both hot and cold reservoirs around an Otto cycle. This will be a finite time heat engine, actually, so we won't actually reach the long time steady state in the operation. But even in finite times, the strong coupling between the system and environment can have a profound effect on the performance of the thermodynamic cycle. So our mapping here, we're still concerned at this point, obviously, just with a single system and a single bath, actually, because around the Otto cycle, the hot and cold bath are never simultaneously coupled to the system. So at this point, we only have coupling to one bath at any time. But we'll come on to the non-additive situation in a couple of slides. So the mapping, so it's incorporated our system reservoir correlations, and I say into a consistent thermodynamic analysis. By that, I mean that at least in the long time limit, we retain a description in terms of thermal states, except of course they're now thermal states in the mapped space, so in the enlarged space of the system plus the collective coordinate. And obviously it circumvents a restriction then of weak coupling and vanishing correlations between the system and the environment. But it also allows us to put forward definitions of heat and work at strong coupling as well. So work is defined here in terms of the enlarged system plus collective mode. So that includes contributions from the interactions. So we can see it as it's defined here. It's a trace over the system plus the collective mode with the Hamiltonian in the enlarged space and the state in the enlarged space between two different points in our cycle or in our general thermodynamic protocol. What that implies is that heat is then defined as the energy that's dissipated into the residual bath. So this is the bath that's coupled to the collective mode after the mapping. And that's the part of the environment that we assume remains in thermal equilibrium. So the part that we treat as having a well-defined thermal state at some given temperature. I guess one consequence of this is that operators for work and heat, well, not operators, in terms of counting statistics for work and heat, for example, the relevant operators should commute with each other, which means that we can say something about the joint statistics of work and heat, even at finite system environment couplings, which is not always the case for other definitions of work and heat that have been put forward in the strong coupling regime. But I'll not go into that today because there's still kind of work in progress on that. So the Otto cycle example, So for those who are unaware, or just as a reminder anyway, the Otto cycle is a 4-stroke heat engine cycle, and it's nice for our purposes because it separates heat and work. So we don't need necessarily to argue about what the appropriate definitions for heat and work should be in the strong coupling regime for the purposes of this cycle anyway. And the cycle proceeds, actually, it's more than 4 strokes in a sense in the strong coupling regime, because we have to also include any energetic exchanges due to coupling and decoupling between the system and environment that are usually ignored in the weak coupling case because they generally evaluate to 0. But these contributions, which we'll consider to be work in this situation, actually evaluate to non-zero contributions for strong coupling. So we start off, say, arbitrarily at this point A primed, where the system has just been coupled to the hot reservoir. The next stroke is a hot isochore, so the system and hot reservoir, the system evolves in contact with the hot reservoir, and there's some exchange of heat, or what we'll term heat anyway, for the purposes of the cycle. At point B, the isochore is finished and the hot reservoir is decoupled from the system to take us to B primed, and there will be an energetic contribution in the strong coupling regime due to that decoupling. From B prime to C, the system is not coupled to any environment, and that's an isentropic expansion stroke. At point C, we couple to the cold environment, again, including any energetic contributions due to the coupling if they exist. And then from C primed to D, it's the cold isochore stroke. And so the system exchanges energy with the cold bath. From D to D primed, we're decoupling from the cold bath. And then from D primed to A, we have an isentropic compression stroke where the system and environments are decoupled. And so that's a work stroke. And then from A to A primed, we couple back to the hot reservoir again. And so that completes the cycle and takes us back to the starting point again. So here's some examples of some performance of the system within the Otto cycle. So on the left-hand side, I'm showing in dashed black with the left axis the power as a function of isochore time, and on the right-hand axis we've got the work as a function of the isochore time. We consider a Hamiltonian that commutes at all time along the isentropic strokes, and so there's no quantum friction effect in our engine. That's because we wanted to isolate any effects due to the system environment correlations and their buildup, rather than quantum friction effects that are already known to exist if the Hamiltonian doesn't commute at all times. And so we just set, because it commutes at all times and there's no quantum friction, we just set the isentropic stroke times to essentially be instantaneous. So they're very fast. And so that's why we're plotting the power and the work as a function of the isochore time instead, which we assume to be the same for both the hot and cold isochores. What we find here is that the power is maximized in a kind of non-equilibrium regime. So that's before the work plateaus. So that seems to be where the power is maximized as a function of isochore time, at least. And if we look at the power, the kind of maximum power as a function of system environment coupling strength, for simplicity, we assume that they're the same for the hot and cold reservoirs, then we find that the power increases with coupling initially, due to the fact that the system approaches equilibrium more quickly, so it exchanges energy with the hot and cold environments more quickly, but that there's some turnover after a certain coupling strength, and so the maximum power occurs at some finite coupling, but it doesn't just increase with coupling. And this turnover is due to the costs, the work costs associated with, in the end, decoupling the system from both the hot and cold reservoirs. So those costs start to dominate for strong coupling, and actually, in the end, completely kill the performance of the engine if the system environment coupling becomes too strong. Now, I mentioned earlier that right near the start that we were going to also look at situations where we have a kind of fully quantum engine, as I've just described, versus a dephased engine, to try and get rid of some of the coherences that build up between the system and the environment. So for a system that's weakly coupled to a reservoir, say the hot, well, it could be the hot or the cold reservoir in the Otto cycle. So if we imagine for a moment that this was a weak coupling, not a strong coupling, then it's straightforward to identify what a purely dephasing environment would be. It would just act in the system, the isolated system energy eigenbasis to kill any coherences that build up within that basis. And that would then not have any energetic contribution, so we could legitimately consider it as being a pure dephasing environment. However, that is not the case when we have strong coupling, because in this situation, with strong coupling, the dephasing environment doesn't commute with the rest of the Hamiltonian. So strictly speaking, it always has an energetic contribution. It's just that we can ignore that contribution for weak enough interactions between the system and the heat reservoir. Now we're not in the weak interaction limit, but our mapping does allow us to define what a dephasing would be without an energetic contribution, even in the strong coupling case. And that's because we now need to dephase in the eigenbasis of the enlarged system plus collective coordinate, which, as I've said, we assume is just weakly coupled to the residual reservoir. So by redefining our thermodynamic system to include the collective coordinate, we can then identify a dephasing environment that doesn't induce any energy exchange at finite heat reservoir coupling. And so it allows us to then probe what the impact is of coherences that build up between our two-level system and the environment through the coherences that are inherent to the mapped system plus collective coordinate. And so we're looking at this here. So on the left-hand side here, I'm showing the work again against isochore time. The black line is the fully quantum or the coherent case that we were looking at in the previous example, and the dashed black line is now the dephased version, where we've introduced a pure dephasing in the way that I just outlined. So that's in the enlarged system plus collective mode eigenbasis, to ensure there's no energetic contribution. What we see in general is that dephased engine outperforms a fully quantum one, but this is not because somehow the costs for decoupling are different. They actually remain essentially the same in both the dephased and the fully coherent engine. It's really because in the dephased case, the system is approaching the steady state, as you can see, more quickly than in the fully coherent states, and so energy exchanges between the system and the reservoirs are happening more quickly, which is advantageous for the performance of the engine. And we can also see this in a parametric plot here of efficiency and power, where we're showing the dephased engine as the dashed lines for different system reservoir coupling strengths, and the solid ones are the fully quantum engine. And as we vary the isochore time here to generate these parametric plots, we can see, for example, that at a given efficiency, the dephased engine is giving us a greater power than the fully quantum engine. So So it does appear that removing these coherences that build up between the system and the environment are advantageous. It is advantageous, at least in this particular Otto cycle example. Okay, how am I doing for time? At this point, I might maybe say a little bit then about non-additivity in situations where we have a kind of natural simultaneous coupling to multiple environments. And hopefully I'll get through this quick enough that there'll be a bit of time for questions afterwards as well. So I've already mentioned situations where we have strong vibrational coupling in the presence of an electromagnetic field. So here I'm considering some two-level emitter, could be a quantum dot, for example, that's weakly coupled to the electromagnetic field, so it can give rise to photon emission into the electromagnetic field, but it's strongly coupled to vibrations, and that's represented by these schematics here showing the vibration, the lattice being displaced in one direction when the system is in its excited state, but when it decays to the ground state, it goes back to its equilibrium. So, for example, that means that we can get things like a phonon sideband in the emission, where rather than just emitting a photon directly into what's termed the zero phonon line, where phonons play no role, the system can emit a phonon and then emit a photon. And so this gives us emission in a sideband to the zero phonon line, which is known as the phonon sideband. So in this example, I'm going to explore what the vibrational impact is on both the kind of spontaneous emission process that I've just mentioned, but also under incoherent, so thermal excitation as well. So our Hamiltonian is fairly straightforward. It's just a two-level system with a ground and an excited state, and then we have a linear coupling to a bath of harmonic oscillators that represents the phonon degrees of freedom, and then a coupling to the electromagnetic field that's written in a rotating wave approximation here, with raising and lowering operators for the field, representing obviously the absorption or emission of photons when the system changes its state. We're going to perform a collective coordinate transformation as before, but only on the system phonon coupling, because that's the coupling we assume to be strong. And then our system Hamiltonian doesn't change, but our phonon coupling is then to the system. Actually, there's a system operator missing there. There should be a projector onto the excited state of the system that couples to our collective coordinate. This is our collective coordinate self-Hamiltonian, and that then defines our mapped system Hamiltonian, so our enlarged Hamiltonian for the system plus the phonon collective coordinate. We're left with a residual bath, and then the terms for the electromagnetic interactions that don't change under the mapping. So a picture sort of schematically to give you a sort of feel for what the physics is here is shown here in A. So what this collective coordinate transformation allows us to do is to associate essentially a vibrational manifold with each of the states of the two-level system. So there's a vibrational manifold associated with the ground state, the two-level system, and then a vibrational manifold associated with the excited state, and there's some displacement between the two due to the non-zero coupling between the system and the phonons. And what we can see immediately is this is going to alter things like the spontaneous emission rate, because the overlap of the vibrational states between the different manifolds is also going to impact how strong the rates are for emission from the excited to the ground state. And I'll compare two cases. So in one case, it's the treatment is additive. So the electromagnetic field is only aware of the two-level, the original two-level system, and is derived with respect to just the two-level system itself. So it's not aware of the strong vibrational coupling. So this is a kind of phenomenological treatment where we would just sort of tack on some dissipator for the electromagnetic environment to a master equation for the system plus vibrational dynamics. In the second case, the fully non-additive case, I'm going to derive the weak coupling terms for the system electromagnetic field interactions in the full eigenbasis of the augmented system. So the two-level system plus the collective phonon coordinate. And then that will be our non-additive treatment where the electromagnetic environment is now aware of the fact that the system is coupled is strongly to vibrations, and so it is aware of this kind of manifold of vibrational states associated with the ground and excited states. So in both cases, actually, the master equation has this form, but remember that rho here is the density operator of the system plus collective coordinate. So it's in the enlarged space. So the system HS primed here is our mapped system Hamiltonian, including the phonon collective coordinate. This is a dissipator for the residual phonon bath, and then this is how we're treating the electromagnetic field. In the additive case, so if we just phenomenologically enforce additivity, that then means that the electromagnetic dissipator takes the standard Lindblad form familiar for quantum optics. So for example, at 0 temperature, it would look like this. But as I've said, in the non-additive case, this dissipator is derived with respect to the enlarged two-level emitter collective coordinate eigenbasis. And so we can see the impact of this here. So on the left-hand side, I'm showing the decay of the two-level system at 0 temperature. Now, in the additive case, so the phenomenological case, all curves lie on top of each other regardless of the system phonon coupling strength. And so the two-level system just decays in the additive case as if it's not impacted by the vibrations at all, which is clearly not the correct physics because the vibrational overlaps should play a role in how strong the transitions are between the two manifolds. And that is captured by the full non-additive approach. And we can see as the coupling strength for the solid lines, which is the non-additive approach, as the coupling strength increases, the decay rate decreases due to suppression from the overlaps of the different manifolds. And that's because the displacement is getting larger and larger for larger and larger coupling strength. And so the overlaps are getting smaller and the rates are reducing as a result. More interestingly, I guess, from a thermodynamic perspective, perhaps, is a plot on the right-hand side where we're showing the steady state two-level system population as the function of system phonon coupling strength. The dashed lines are the additive case here, and the solid lines are the non-additive. And what we can see, apart from an interesting kind of possibility of population inversion in the steady state for the non-additive case, is that the additive approach just equilibrates with respect to the electromagnetic field. So the electromagnetic field here is at non-zero temperature. So going from blue to red is going from colder to hotter temperatures here. So there's some thermal excitation. So it completely misses the non-equilibrium physics of the full non-additive approach, where we've got a competition in the long time limit between the system attempting to equilibrate with the electromagnetic field and with the phonons that held at the two were held at different temperatures. So we end up with a non-equilibrium situation that the additive approach just can't capture. Okay, I'm aware I'm running a bit low on time, and I wanted to take some questions if there were any, but very briefly, I'll just mention that we can do similar things for the case of counting statistics in transport problems. So here we've got a double quantum dot system that's weakly coupled to a left and right lead that give rise to current through the system. They're held at some different bias voltage here in this example, and then we've got strong coupling of the dots to phonons in the central region. Again, we can compare additive versus non-additive approaches. So the additive approach, as before, we assume that the leads are only aware of the system itself, not of the mapped double dot system plus phonon collective coordinate. And in the non-additive case, the lead influence is derived with respect to the full enlarged eigenbasis of the system plus the collective mode. So the additive approach is, again, a kind of phenomenological approach. And we apply full counting statistics in this case to track electron flow in the steady state. So here's a couple of examples. So in the infinite bias limit, actually, the non-additive and the additive approaches agree with each other. So this is current as a function of system phonon coupling strength. And we can see the two lie on top of each other. A Born-Markov weak coupling approach that treats also the phonons as weakly coupled works well at weak coupling, but then plateaus at stronger coupling and doesn't capture both this increase in current, but also the blockade effect, Frank condom blockade, as it's termed, where the current drops to zero at strong phonon coupling. Again, that's because of the suppression of overlaps between vibrational states in the strong coupling limit. So that's fine at infinite bias, but worryingly, at zero bias, where we expect no current, which is indeed true of the non-additive and the Born-Markov approaches, we get an unphysical current at strong coupling in the additive approach. And that's because the leads are not properly aware of the strong vibrational coupling. And so they effectively see an induced bias due to the vibrational coupling that's not really there. And we need the full non-additive approach to correctly account for the fact that the situation really is a zero bias situation where we'd expect no current to flow because the electron and phonon temperatures are set to be equal here. We can also look at the opposite situation where we have no bias, but we have a thermal gradient between the leads and the vibrations. So here the system is acting as a thermoelectric. So we've got hot phonons that are a resource to allow electrons. Sorry, I said no bias before. I didn't mean that. I meant a kind of reverse bias where there's a gradient, a bias from left to right. So the hot phonons are a resource that allow electrons to overcome that chemical potential gradient and tunnel from left to right. And so this is a thermoelectric regime. And again, we can compare an additive and non-additive approach. This is the efficiency as a function of bias voltage. What we can see is in the full strong coupling case, actually the efficiency increases, but not up to the Carnot limit, and actually decreases down to zero as we reach the stopping voltage. And so the behavior is actually qualitatively different to the weak coupling case, which is the dashed line, which reaches Carnot at the efficiency at the stopping voltage. So when the power goes to zero. Again, the additive case can give rise to non-physical effects such as efficiencies beyond the Carnot bound. So that's shown in more detail in the inset, where because the stopping voltage is different in the additive case, we see that it can break the Carnot bound, which is an unphysical artifact of the additive approximation. And just because we had some discussion, some very nice discussion yesterday on thermodynamic uncertainty relations, I thought I'd show the relative uncertainty here, so we can probe higher cumulants with the counting statistics techniques. So the relative uncertainty, as it was introduced yesterday, is a ratio of the noise, the second order cumulant, to the square of the current, the first order cumulant. And it's constrained by thermodynamic uncertainty relations, or steady state thermodynamic uncertainty relations, by the entropy production. So in this context, the thermoelectric context, that implies that if we want to try and reach Carnot efficiency, at least in the weak coupling case, that will come at the cost of diverging fluctuations. And we can see that here. So this is a plot of relative uncertainty against efficiency as we're sweeping the full bias range for which the system acts as a thermoelectric. And we can see that the weak coupling approach, which is dashed here, reaches Carnot, but with diverging fluctuations. in the strong coupling case, the non-additive case, actually, it doesn't reach Carnot, and the efficiency actually drops, but the fluctuations still diverge. And then the right-hand side is a magnification around here, where we can see that, again, that the additive approach is incorrectly predicting efficiencies above the Carnot bound as we go towards the stopping voltage. Okay, so I think I've run out of time. So I'll just leave up a summary in terms of pictures and some references if anyone's interested in them. And I should just acknowledge my colleagues who I've worked with on this work, and also funding from the EPSRC. So thanks very much for your attention.
Thank you very much, Ashan. It has been a very nice talk. It's true that we are running out of time, but I think we have time for one or two quick questions. So if anyone has it, please, you can use the hands up button on Zoom or just write it in the chat. Well, it seems that you have given a very clear talk.
Well, either that or it's so unclear that no one knows what question to ask.
I'm sure it's the first one. Yes, there is a question for you, actually. Kay, would you like to unmute yourself and just go for it?
Yes. Yes, thanks for the talk. It was very nice. I got a very quick question. So how do you know in general that after you've done this reaction coordinate mapping, your system bath coupling is weaker than before? Does this require specific Hamiltonian, or is this a generic feature of these harmonic reservoirs?
So that's an interesting question, actually. So you don't always know that it's weaker than before. And of course, actually, I've looked at situations where it works well, but it's not guaranteed to work well, because it's still, I mean, the mapping is unitary, so that's fine, but the approximations we make after the mapping could break down if we're not in an advantageous situation. What tends to happen, actually, which is interesting, is that really it's the bath correlation functions after the mapping that change significantly, and it tends to make the Markov approximation much more valid, because the correlation functions become short-lived, even if they were originally longer-lived for the pre-mapping. And so the coupling strength itself is less important. In fact, I think the coupling strength maybe doesn't come into the spectral density after the mapping to the residual bath. I'll have to check on that, but it's more determined by things like bath cutoff frequencies in the spectral density. And so what you need is situations where the mapping takes you to a situation where the Markov approximation becomes very well justified on the residual environment, because the correlations become very short-lived.
Okay, thank you. Could I actually do that for different environments, or is it specific for these bosonic harmonic modes?
No, you can map anything really, and others like Philip Strasberg and Gernot Schaller have done it for fermionic environments as well. So in the transport case, actually, one thing Connor and I wanted to do but didn't have time to do during his PhD was map leads and phonons to look at interferences in strong coupling between fermionic and bosonic degrees of freedom. So I guess that would be something that would be on the list of calculations to do at some point.
Okay, brilliant. Thank you very much.